Imagine a place in the universe so dark, so dense, so utterly consuming that not even light itself can escape its grasp. This is not the realm of science fiction, but the cold, mathematical reality of black holes, objects so extreme that they challenge our very understanding of existence itself. In the depths of space, these cosmic monsters lurk in the darkness, warping the fabric of reality around them like massive bowling balls pressing down on a stretched rubber sheet. The story begins with the death of giants. When a star at least 25 times more massive than our Sun reaches the end of its life, it faces a catastrophic fate unlike anything we can imagine on Earth. For millions of years, this stellar behemoth has maintained a delicate balance, with the outward pressure of nuclear fusion holding back the crushing grip of its own gravity. Picture the star as a cosmic battlefield where two fundamental forces wage war. In the core, temperatures soar to over 100 million degrees Celsius as hydrogen atoms smash together to form helium, releasing tremendous energy that pushes outward. Meanwhile, gravity relentlessly pulls inward, trying to collapse the entire star into a point. This balance is precarious, like a person standing on a tightrope in a hurricane. The star burns through its nuclear fuel at a staggering rate, converting millions of tons of matter into energy every single second. First, hydrogen becomes helium, then helium fuses into carbon and oxygen, then these heavier elements forge into silicon, and finally silicon burns into iron. But iron is different. Iron is the end of the line. When iron atoms try to fuse, they don't release energy, they absorb it. The nuclear fires that have sustained the star for millions of years suddenly go out like a candle in the wind. What happens next unfolds in mere seconds, yet the consequences echo through space-time itself. The star's core, no longer supported by the fierce energy of fusion, begins to collapse under its own immense weight. The outer layers, suddenly unsupported, crash inward at speeds that defy comprehension. First 25,000 kilometers per hour, then 50,000, then 100,000 kilometers per hour. The collapse accelerates beyond anything in human experience. In less than a second, a core larger than Earth compresses to a sphere smaller than Manhattan, then smaller than a city block, then smaller still. The physics of this collapse pushes matter into states that exist nowhere else in the universe. Electrons, those fundamental particles that orbit atomic nuclei, get crushed together with protons to form neutrons. Atoms, which make up everything we know and love, simply cease to exist as distinct entities. The matter becomes so dense that a teaspoon of it would weigh as much as Mount Everest. Yet even this is not the end. If the stellar core contains enough mass, not even the pressure of neutrons pushing against each other can halt the collapse. The mathematics of this collapse were first understood by Karl Schwarzschild, a German physicist and astronomer whose story reads like a tragic novel. Schwarzschild was serving as a soldier on the Russian front during World War I, when Einstein published his theory of general relativity in 1915. While his comrades fought in the trenches, Schwarzschild worked by candlelight in his tent, solving Einstein's incredibly complex field equations. Within months, he had found an exact solution that described the space-time around a spherically symmetric mass. Tragically, Schwarzschild died of an autoimmune disease just months after making his groundbreaking discovery in 1916, never living to see how profoundly his work would reshape our understanding of the cosmos. He was only 42 years old. His solution, scribbled in notebooks amid the chaos of war, would eventually reveal the existence of some of the most extreme objects in the universe. Schwarzschild's solution revealed something extraordinary and terrifying. For any object, there exists a critical radius, now called the Schwarzschild radius, where gravity becomes so intense that the fabric of space-time itself tears. This isn't just strong gravity, it's gravity so powerful that it bends space-time into a shape that traps everything, even light itself. Calculate this radius for our Sun, and you get about 3 kilometers. For Earth, it's less than a centimeter. For a star 25 times more massive than our Sun, it might be 75 kilometers across. This boundary, known as the event horizon, marks the point of no return. The name itself carries an ominous weight. An event is something that happens at a specific place and time. The horizon is as far as you can see. Beyond the event horizon, no events can ever be observed from the outside universe. It's a one-way membrane in space-time itself. Cross this invisible line, and you can never come back. Not if you're the most advanced spaceship ever conceived. Not if you're light traveling at 300,000 kilometers per second. Not even if you're information itself about what you once were. The event horizon isn't made of anything physical. There's no wall, no barrier, no sign that says point of no return. It's simply a mathematical consequence of extreme gravity. Space and time become so warped that all possible paths lead inward. Imagine trying to climb out of a hole where the walls are constantly growing steeper and higher. Eventually, you reach a point where even if you could run at the speed of light, you still couldn't escape. That's the event horizon. For our dying star, if its core contains more than about 3 times the mass of our Sun, nothing in the known universe can stop the collapse. The matter doesn't just compress, it transcends the normal rules of physics entirely. Quantum mechanics, which governs the behavior of atoms and particles, breaks down. The equations that describe electromagnetic forces become meaningless. Even the concept of temperature loses its definition. At the center of this cosmic catastrophe, all the mass gets crushed into what physicists call a singularity, a point of theoretically infinite density where the laws of physics as we know them simply break down. It's not just that we don't know what happens at the singularity, it's that the very questions we might ask become meaningless. What is the temperature of infinity? What is the size of a point? What happens when all the matter in a region the size of a city gets compressed into a space smaller than an atom? The singularity represents the ultimate frontier of human knowledge. It's a place where mathematics itself seems to give up, where equations spit out infinities and impossibilities. Some physicists believe the singularity is a sign that our theories are incomplete, that some new physics kicks in before matter can be compressed to truly infinite density. Others think the singularity is real, a place where the universe creates something genuinely new and impossible to understand with current knowledge. But here's where black holes begin to defy not just common sense, but our deepest intuitions about reality itself. According to Einstein's theory of general relativity, time itself behaves strangely near a black hole. Time isn't the steady, universal metronome we experience in everyday life. Near a black hole, time becomes elastic, stretching and compressing in ways that challenge our most basic assumptions about reality. As you approach the event horizon, time slows down relative to distant observers. This isn't science fiction, it's a mathematical certainty. To someone watching from far away, you would appear to slow down as you fall toward the black hole. Your movements would become sluggish, your watch would tick more slowly, your very thoughts would appear to decelerate. As you reach the event horizon, you would appear to freeze completely, suspended forever at the edge of the cosmic abyss. To the distant observer, your image would grow redder and dimmer as gravity stretches the wavelengths of light leaving your body. Eventually, you would fade from view entirely, not because you disappeared, but because the light from your frozen form would be stretched to wavelengths too long for any instrument to detect. From the outside universe's perspective, you would remain forever suspended at the event horizon, a ghostly reminder of what was lost to the black hole's hunger. But from your perspective, the experience would be entirely different. You would fall through the event horizon in finite time, perhaps just a few seconds, for a black hole with the mass of our Sun. You wouldn't feel anything special as you cross the event horizon. There would be no barrier, no sensation of passing through a boundary. Space would look normal around you, perhaps even empty. The stars would still shine, though they might appear strangely distorted. However, as you continued to fall inward, you would begin to experience what physicists coldly term spaghettification. The gravitational field near a black hole isn't uniform. Your feet, being closer to the center, would experience stronger gravity than your head. This difference, called a tidal force, would stretch you vertically while compressing you horizontally. For a black hole with the mass of our Sun, these tidal forces would become lethal long before you reach the event horizon, stretching your body like taffy until it literally came apart. For more massive black holes, the ones lurking at the centers of galaxies, with masses millions or billions of times greater than our Sun, the tidal forces at the event horizon are gentler. You might survive crossing the boundary intact, only to be torn apart closer to the singularity. The bigger the black hole, the more gently it kills you, at least initially. The event horizon represents more than just a boundary in space. It represents a boundary in causality itself. Causality is the principle that causes precede their effects, that events in the past can influence the future, but not vice versa. It's so fundamental to our understanding of reality that we rarely even think about it, but black holes challenge even this basic assumption. Events that happen inside the event horizon can never influence events outside. Information about what occurs beyond the boundary can never reach the external universe. It's as if a portion of the universe has been permanently severed from the rest of reality, sealed away behind an impenetrable veil of gravity. This creates a cosmic censorship, hiding the most extreme physics in the universe from outside observation. This creates a profound puzzle that strikes at the heart of how we understand the universe. In our everyday experience, information is never truly lost. Drop a glass and watch it shatter, and while the glass can never be perfectly reconstructed, all the information about its original state still exists in principle. It's encoded in the motion of every fragment, the vibrations in the air, the heat generated by the impact. The information has been scrambled beyond practical recovery, but it hasn't vanished. Burn a book, and while the words disappear, the information about those words still exists in the arrangement of smoke particles, the infrared radiation carrying heat away, the chemical changes in the ashes. Given perfect knowledge of every particle and wave, a sufficiently advanced being could in principle reconstruct the original text. The information becomes practically inaccessible, but it remains theoretically present. Scramble an egg, and while you can't unscramble it practically, the information needed to reverse the process still exists in the motion and position of every protein molecule. Mix cream into coffee, and while the cream disperses irreversibly, the information about its original state persists in the microscopic details of the mixture. This principle, known as information conservation, isn't just a philosophical idea or a convenient assumption. It's baked into the fundamental mathematical structure of quantum mechanics, the theory that describes the behavior of atoms, particles, and the smaller scales of reality. Every quantum process, no matter how complex or chaotic it appears, must in principle be reversible. The information that describes the quantum state of a system cannot simply vanish into nothingness. This isn't just a scientific preference or a theoretical convenience. It's a mathematical requirement for the consistency of quantum theory itself. The equations of quantum mechanics are what mathematicians call unitary, meaning they preserve information. If information could be destroyed, the mathematical foundation of quantum mechanics would collapse like a house of cards. But black holes seem to mock this sacred principle. When matter falls past the event horizon, it appears to take all information about its quantum state with it into a realm that can never communicate with the outside universe. The black hole grows slightly more massive, and its event horizon expands slightly. but it reveals nothing about what it has consumed. A black hole formed by swallowing an entire library, complete with every book ever written, would be identical in every measurable way to one formed by swallowing an equal mass of hydrogen gas. All the information that made each piece of infalling matter unique, all the quantum numbers that distinguished one particle from another, all the complex arrangements that encoded meaning and structure, appear to be lost forever behind the event horizon. This apparent violation of information conservation creates what physicists call the information paradox, a puzzle that has tormented theoretical physicists for decades. If information can truly be destroyed by black holes, then quantum mechanics, one of the most successful and precisely tested theories in the history of science, must be fundamentally wrong. The theory that explains everything from computer chips to stellar fusion, from MRI machines to the stability of atoms themselves, would need to be abandoned or radically modified. But if information cannot be destroyed, then our understanding of black holes, based on Einstein's equally successful theory of general relativity, must be incomplete or incorrect. General relativity has passed every experimental test, from predicting the orbit of Mercury to detecting gravitational waves from colliding black holes. It's the foundation of our understanding of the cosmos, from the Big Bang to the expansion of the universe. The information paradox forces us to choose between two of our most successful theories, or to find some way to reconcile them that preserves the essential insights of both. It's like being asked to choose between your left arm and your right arm when you need both to function. The stakes of this paradox extend far beyond academic physics. Information conservation is tied to our understanding of time, causality, and the very nature of physical law. If the universe can erase information, then the past becomes uncertain. The future becomes unpredictable in a new and fundamental way, and reality itself becomes less solid than we believed. In classical physics, if you knew the position and momentum of every particle in the universe, you could in principle calculate both the entire future and the entire past. This is called determinism, the idea that the present state of the universe uniquely determines all future and past states. Quantum mechanics introduced uncertainty at the smaller scales, but preserved a form of determinism in the evolution of quantum states. If black holes can destroy information, then even this quantum determinism breaks down. The universe becomes fundamentally unpredictable, not just because we lack knowledge, but because knowledge itself can be annihilated. The past becomes unknowable, not because it's hidden, but because it may have been erased from reality itself. As we stand on the edge of this conceptual abyss, we face questions that probe the deepest foundations of existence. Are black holes cosmic recycling centers that transform information rather than destroying it? Are they repositories where information is stored in ways we don't yet understand? Do they represent windows into higher dimensions where information continues to exist in forms we cannot perceive? Or do they represent something far stranger, places where our most basic assumptions about the universe simply don't apply? Perhaps information can be destroyed, and we need to learn to live in a cosmos less certain and more mysterious than we ever imagined. The search for answers has driven physicists to the very limits of human knowledge, forcing us to reconsider everything we think we know about space, time, matter, and information itself. They have proposed radical ideas that challenge our understanding of reality. Maybe black holes aren't the smooth, empty regions that Einstein envisioned, but seething walls of fire that incinerate anything that approaches. Maybe information doesn't fall into black holes at all, but gets encoded on their surfaces in ways too subtle for us to detect. In the cosmic darkness of black holes, we confront not just the death of stars, but potentially the death of certainty itself. These objects force us to grapple with the most fundamental questions about the nature of existence. What is information? Can it truly be destroyed? What does it mean for something to exist if no trace of it can ever be recovered? The question that haunts every physicist who studies these objects is simple yet profound. If nothing escapes a black hole's grasp, what happens to the information that falls in? This question has sparked decades of intense debate, revolutionary new theories, and a complete re-examination of our understanding of space, time, and reality itself. And if we can't answer that question, what does it mean for everything we think we know about the universe we inhabit? When most people hear the word information, they think of newspapers, websites, or conversations with friends. But in the realm of physics, information means something far more fundamental and mysterious. It represents the complete description of reality itself, encoded in ways that would seem alien to our everyday experience, yet govern every aspect of the universe around us. To understand what physicists mean by information, imagine you could freeze time and examine every particle in a simple system, say a coin spinning through the air. Classical physics would tell you that if you knew the exact position, velocity, and rotation of that coin at any given moment, you could predict with perfect accuracy where it would land. The information about the coin's future is completely contained in its present state. This seems obvious, but it hints at something profound about the nature of reality itself. Now scale this idea up to the entire universe. In principle, if you could measure the position and momentum of every single particle, from the electrons in your body to the plasma in distant stars, you would possess complete information about the cosmos. This information would allow you to calculate not just the future of the universe, but also its entire past. The present moment would contain within it the seeds of all possible futures and the echoes of all possible histories. This classical view of information faced its first challenge in the early 20th century with the birth of quantum mechanics. Werner Heisenberg discovered his famous uncertainty principle in 1927, showing that you cannot simultaneously know both the exact position and momentum of a particle. This wasn't just a limitation of measurement technology, it was a fundamental property of reality itself. Nature, it seemed, had built uncertainty into its very foundation. But quantum mechanics didn't abandon the concept of complete information, it transformed it. Instead of describing particles as having definite positions and velocities, quantum theory describes them using wave functions, mathematical objects that encode all possible information about a quantum system. The wave function doesn't tell you where a particle is, but rather where it might be, and with what probability you'll find it there. Consider an electron orbiting an atomic nucleus. In classical physics, you might imagine it following a definite path, like a planet orbiting the sun. But quantum mechanics reveals something far stranger. The electron exists in what physicists call a superposition, occupying all possible orbits simultaneously until someone measures it. The wave function describing this electron contains information about every possible state it could be in, weighted by the probability of finding it there. This quantum information is far richer and more complex than its classical counterpart. Where classical information might require a few numbers to describe a particle's state, quantum information can require an infinite amount of data to fully specify a wave function. Yet this information follows strict mathematical rules that preserve its total content over time. The mathematics of quantum mechanics is built on a foundation called unitarity, a principle that ensures information is never created or destroyed, only transformed. Think of it like a cosmic accounting system where the books must always balance. Every quantum process, from the decay of a radioactive atom to the collision of particles in an accelerator, must conserve the total amount of information in the system. This conservation isn't just a convenient assumption, it's a mathematical necessity. The equations that govern quantum evolution, known as the Schrödinger equation, are reversible. Given complete information about a quantum system at any moment, you can calculate its state at any other time, past or future. This reversibility is what allows quantum computers to perform certain calculations exponentially faster than classical computers by exploring multiple computational paths simultaneously. But quantum information conservation goes deeper than mathematical elegance. It connects to our understanding of time itself. In physics, the arrow of time, the reason we experience past, present, and future as distinct, emerges from the second law of thermodynamics. This law states that entropy, a measure of disorder, always increases in isolated systems. Hot coffee cools down, mixed gases don't spontaneously separate, and scrambled eggs don't unscramble themselves. Yet at the microscopic level, the fundamental laws of physics are time reversible. The equations describing individual particles work equally well running forward or backward in time. The apparent irreversibility of macroscopic processes emerges from the statistics of dealing with enormous numbers of particles. It's not that the microscopic information is lost, it's that tracking it becomes practically impossible. This creates a beautiful picture of physical reality. Information at the quantum level is perfectly conserved and reversible. But when you have countless particles interacting, their information becomes so scrambled and distributed that macroscopic processes appear irreversible. It's like trying to unscramble an egg by tracking the motion of every protein molecule. Theoretically possible, but practically impossible. The connection between information and thermodynamics became clearer in 1961, when Rolf Landauer, a physicist at IBM, proved that erasing information requires energy. Every time you delete a file from your computer, clear your browser history, or even forget someone's name, the physical process of erasing that information generates heat. This isn't a design flaw, it's a fundamental law of nature. Landauer's principle reveals that information and energy are intimately connected. Information has mass, occupies space, and follows conservation laws just like energy and momentum. A hard drive with data weighs more than an empty one. Though the difference is incredibly tiny, the information stored in your brain contributes to your mass, though again by an amount far too small to measure with any scale. This deep connection between information, energy, and thermodynamics led to revolutionary insights about the nature of physical law. John Wheeler, one of the most influential physicists of the 20th century, coined the phrase "it from bit" to express his belief that all physical entities are information-based. In Wheeler's vision, particles, forces, and even space-time itself might be emergent properties of more fundamental informational structures. Claude Shannon, working at Bell Labs in the 1940s, developed information theory to solve practical problems in telecommunications. He wanted to know the maximum amount of information you could transmit over a noisy communication channel. Shannon's work revealed that information could be quantified precisely using mathematical concepts borrowed from thermodynamics. Shannon defined information content in terms of surprise or uncertainty. A message that tells you something you already knew carries no information. A message that resolves maximum uncertainty carries maximum information. This led to the famous formula connecting information content to probability, measured in units called bits. 1 bit represents the information gained by learning the answer to a yes or no question with equal probability for each answer. Shannon's information theory seemed at first to be purely practical, relevant only to engineers designing telephone networks and computer systems. But physicists soon realized that Shannon information was intimately connected to thermodynamic entropy, the quantity that measures disorder in physical systems. In fact, they turned out to be essentially the same thing, connecting information theory to fundamental physics in unexpected ways. This connection became crucial when physicists began studying black holes seriously in the 1970s. If black holes behave like thermodynamic systems, with temperature and entropy, then they must also be related to information in Shannon's sense. But what information could a black hole possibly contain? And how could that information be accessed or measured? Jacob Bekenstein, working as a graduate student under John Wheeler, made a stunning proposal in 1972. He suggested that black holes have entropy proportional to the area of their event horizons, not their volume as you might expect. This meant that the information content of a black hole was encoded somehow on its two-dimensional surface, not in its three-dimensional interior. Bekenstein's proposal was initially controversial. How could three-dimensional objects falling into a black hole have their information encoded on a two-dimensional surface? It seemed to violate basic intuitions about geometry and space. Yet Bekenstein's formula gave the right answer when applied to thought experiments involving black holes and information. The Bekenstein bound, as it came to be known, placed fundamental limits on how much information could be stored in any region of space. These limits were far more restrictive than anything classical physics suggested. According to Bekenstein, there was a maximum amount of information that could fit in your living room, your city, or even the observable universe itself. These information-theoretic insights revealed that space, time, and matter might not be as fundamental as physicists had assumed. Instead, they might be emergent properties of more basic informational structures. Reality might be, in Wheeler's phrase, made of information all the way down. But this raised profound questions about the nature of physical existence. If information is fundamental, what happens when it appears to be destroyed? In everyday thermodynamics, information doesn't disappear, it just becomes practically inaccessible. The information about the original arrangement of molecules in a broken egg still exists. It's just scrambled beyond practical recovery. Yet black holes seem to present a different situation entirely. Information falling past the event horizon didn't just become scrambled or hidden, it appeared to be cut off from the rest of the universe forever. No conceivable measurement or calculation could recover it. This wasn't just practical inaccessibility, it seemed like genuine destruction. The problem became acute when considering quantum mechanics. Quantum information is far more fragile than classical information. In classical physics, you can copy information perfectly. You can photocopy a document, duplicate a file, or memorize a poem without destroying the original. But quantum mechanics forbids perfect copying of unknown quantum states. This no-cloning theorem means that quantum information cannot be duplicated, only moved or transformed. If quantum information cannot be copied, then its destruction becomes far more serious. Classical information can in principle always be reconstructed from multiple sources. Even if you burn a library, copies might exist elsewhere. But quantum information is unique. Destroy it, and it's gone forever with no possibility of recovery or reconstruction. This uniqueness of quantum information makes black holes particularly threatening to the foundations of physics. When quantum systems fall into black holes, they seem to take with them unique information that cannot exist anywhere else in the universe. This apparent destruction of irreplaceable quantum information struck at the heart of quantum mechanics itself. The debate over information destruction in black holes forced physicists to confront fundamental questions about the nature of reality. Is information truly fundamental, more basic than matter and energy? Can information actually be destroyed, or does it always find a way to survive in some form? If information is lost, what does that mean for our understanding of time, causality, and physical law? These questions became more than academic when Stephen Hawking made his revolutionary discovery about black hole radiation in 1974. Hawking's work suggested that black holes aren't perfectly black after all, but slowly evaporate by emitting thermal radiation. This discovery promised to resolve the information paradox, but instead made it infinitely worse. If Hawking was right, black holes would eventually disappear completely, taking with them all the information that ever fell inside. This wasn't just information being hidden behind an event horizon. It was information being erased from the universe entirely. The implications were staggering, threatening to undermine the mathematical foundations of quantum mechanics and our understanding of physical reality itself. The stage was set for one of the most profound conflicts in the history of physics, a battle between two of our most successful theories over the ultimate nature of information and reality. Black holes had posed a challenge that would force physicists to question everything they thought they knew about the universe. The year was 1974, and Stephen Hawking was a young physicist at Cambridge University, already battling the motor neuron disease that would eventually confine him to a wheelchair. Working alone in his office, armed with nothing but pen, paper, and one of the most brilliant minds in physics, Hawking was about to detonate an intellectual bomb that would shatter everything physicists thought they knew about black holes and shake the very foundations of modern physics. Hawking's journey to this revolutionary discovery began with a deceptively simple question. He wanted to understand what happened when you combined Einstein's theory of general relativity with quantum mechanics, the strange world of subatomic particles and probability waves. Most physicists avoided this combination because the mathematics became impossibly complex. But Hawking possessed an almost supernatural ability to see through mathematical complexity to the physical truth beneath. The stage for Hawking's discovery was set by the peculiar nature of empty space itself. To most people, a vacuum means nothing, an absence of matter and energy. But quantum mechanics reveals that empty space is anything but empty. It seethes with activity, filled with virtual particles that pop into existence and annihilate each other in times so brief that they exist in a quantum twilight between reality and non-existence. These quantum fluctuations aren't just theoretical curiosities. They have measurable effects in the real world. They alter the energy levels of electrons in atoms, create tiny forces between metal plates in vacuum chambers, and contribute to the fundamental constants that govern the behavior of matter and energy. The vacuum is alive with quantum activity, a roiling foam of potential existence. Hawking realized that something extraordinary might happen when this quantum vacuum encountered the extreme environment near a black hole's event horizon. The gravitational field near a black hole is so strong that it warps not just space and time, but the very fabric of the quantum vacuum itself. Virtual particles that would normally annihilate each other might be torn apart by the black hole's immense gravity. The key insight came from understanding how gravity affects the quantum vacuum near the event horizon. Imagine virtual particle pairs constantly appearing throughout space, each pair consisting of a particle and its antiparticle. Normally, these pairs quickly find each other and annihilate, returning the borrowed energy to the vacuum and maintaining the cosmic balance sheet. But near a black hole's event horizon, something dramatic can happen. The intense gravitational field can separate these virtual pairs before they have a chance to annihilate. One member of the pair might fall past the event horizon and disappear forever, while its partner escapes to infinity as a real particle. The black hole, in effect, promotes virtual particles to real existence by preventing their mutual annihilation. This process, now known as Hawking radiation, requires the black hole to pay an energy cost. When a virtual pair separates near the event horizon, the black hole must provide the energy to make both particles real. Since energy and mass are equivalent according to Einstein's famous equation E equals mc squared, this energy payment comes at the cost of the black hole's own mass. Hawking's calculations revealed something astounding. Black holes aren't perfectly black after all. They glow with thermal radiation, emitting photons and other particles at a temperature that depends on their mass. The smaller the black hole, the hotter it gets. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. But the temperature relationship is inverse and extreme. A black hole with half the mass of our Sun would be twice as hot. One with 1,000th the mass would be 1,000 times hotter. Black holes the size of mountains would glow white-hot, while microscopic black holes would burn with temperatures exceeding those in the cores of the most massive stars. This temperature dependence led to a startling conclusion. As black holes emit Hawking radiation, they lose mass and shrink. As they shrink, they get hotter. As they get hotter, they emit radiation faster and lose mass more quickly. This creates a runaway process where small black holes evaporate at an accelerating rate, eventually exploding in a final burst of energy. For stellar mass black holes, this evaporation process is incredibly slow. A black hole with the mass of our Sun would take longer than 10 to the 67th years to evaporate completely, a time so vast that it makes the current age of the universe, a mere 14 billion years, seem like the blink of an eye. The observable universe would have expanded, cooled, and died countless times over before such a black hole would disappear. But Hawking's discovery implied that smaller black holes, if they existed, would evaporate much more quickly. A black hole with the mass of a mountain would disappear in less than a second, releasing energy equivalent to millions of hydrogen bombs. Even smaller black holes would vanish in microseconds or nanoseconds, their brief existence ending in spectacular explosions. The physics behind Hawking radiation is subtle and counterintuitive. Unlike the light from a star, which carries information about the star's composition, temperature, and internal processes, Hawking radiation appears to be perfectly thermal. Thermal radiation is the most random, information-free form of energy possible. It's like the static you see on an old television tuned to an empty channel, pure noise with no encoded information whatsoever. This thermal nature of Hawking radiation was not an accidental detail. It was central to Hawking's analysis. He calculated that the radiation emerging from a black hole would have exactly the same properties as radiation from any other object at the same temperature. A black hole that had swallowed Shakespeare's complete works would emit identical radiation to one that had consumed an equal mass of hydrogen gas. This prediction struck at the heart of what physicists understood about information and thermodynamics. In all other physical processes, information might become scrambled or hidden, but it was never truly destroyed. Burn a book, and the information about its contents becomes encoded in the motion of smoke particles and heat radiation. In principle, with perfect knowledge and unlimited computational power, you could reconstruct the original text. But Hawking radiation seemed different. It appeared to carry no information about what had fallen into the black hole. The radiation was purely thermal, containing only information about the black hole's mass, angular momentum, and electric charge. Everything else that made the infalling matter unique seemed to vanish without a trace. Consider the implications. Drop an encyclopedia into a black hole, and according to Hawking's analysis, the resulting radiation would be indistinguishable from that produced by dropping in an equal mass of cosmic dust. The information content of millions of pages of text would simply disappear from the universe, erased as thoroughly as if it had never existed. This information destruction becomes even more dramatic when you consider black hole evaporation. As a black hole radiates away its mass, it eventually disappears completely. At that point, there's nothing left to encode information about what fell in originally. The information doesn't just become inaccessible, it appears to be annihilated entirely, removed from physical reality forever. Hawking himself initially embraced this conclusion. In 1976, just 2 years after his original discovery, he argued that black holes represent the first known physical process that actually destroys information. This wasn't just information becoming scrambled or hidden. It was genuine information death, the permanent removal of knowledge from the universe. The implications were staggering. If information could be truly destroyed, then the fundamental equations of quantum mechanics would need to be modified or abandoned. Quantum theory's mathematical structure depends crucially on the principle that information is conserved. Remove that principle, and the entire theoretical edifice becomes inconsistent. This wasn't just an abstract mathematical problem. Information conservation is intimately connected to the predictability of physical processes. In a universe where information can be destroyed, the future becomes fundamentally unpredictable, not just because we lack knowledge, but because knowledge itself can be annihilated. Consider what this means for causality, the principle that causes precede their effects. If information about past events can be destroyed, then the causal chain linking past and future becomes broken. The universe would become fundamentally uncertain in a new and unprecedented way, where not even perfect knowledge of present conditions could determine future outcomes. The scientific community's reaction to Hawking's proposal was explosive. Some physicists embraced it as a revolutionary insight that would lead to new physics beyond quantum mechanics. Others rejected it as impossible, arguing that information conservation was too fundamental to abandon. The debate split the physics community into warring camps, each armed with mathematical arguments and philosophical convictions. John Preskill, a theoretical physicist at Caltech, emerged as one of the most articulate defenders of information conservation. He argued that quantum mechanics was too successful and too deeply tested to be abandoned lightly. The theory had explained everything from the behavior of atoms to the operation of lasers and computer chips. Its mathematical consistency and experimental success made it one of the crown jewels of human knowledge. Preskill and others argued that Hawking's analysis, brilliant as it was, must be incomplete. Perhaps the calculation missed some subtle quantum effects that would allow information to escape with the Hawking radiation. Maybe the radiation wasn't perfectly thermal after all, but contained hidden correlations that encoded information about the black hole's contents. Leonard Susskind, a physicist at Stanford University, became another vocal critic of information destruction. He argued from a more fundamental perspective, claiming that information loss would violate basic principles of quantum mechanics in ways that would make the entire theory mathematically inconsistent. In Suskind's view, accepting Hawking's conclusion would require physicists to abandon one of their most successful theories, but Hawking had powerful allies as well. Kip Thorne, his colleague and frequent collaborator, supported the information loss hypothesis. Thorne argued that general relativity was equally successful and well tested as quantum mechanics. If the two theories came into conflict, there was no a priori reason to favor quantum mechanics over relativity. The debate raged for decades, with neither side able to deliver a knockout blow. Hawking's original calculation was mathematically rigorous within its assumptions, but those assumptions might be violated by effects too subtle to capture in the initial analysis. The quantum mechanical arguments for information conservation were compelling, but they relied on extending familiar principles into the unprecedented regime of black hole physics. As the controversy deepened, it became clear that the stakes were higher than anyone had initially realized. The black hole information paradox wasn't just a technical problem in theoretical physics. It was a fundamental challenge to our understanding of physical reality. The resolution would require new insights into the nature of space, time, information, and quantum mechanics itself. Experimental tests seemed impossible. Stellar mass black holes emit Hawking radiation so slowly and at such low temperatures that detecting it is far beyond current technology. The radiation would be completely overwhelmed by other sources of background energy in the universe. Even the most sensitive instruments conceivable would be unable to measure Hawking radiation directly. This experimental inaccessibility meant that the debate had to be resolved through pure theoretical reasoning, mathematical calculation, and logical argument. physicists found themselves in the unusual position of trying to understand one of nature's most fundamental processes without any possibility of direct experimental verification. Meanwhile, the implications of the paradox continued to ripple through theoretical physics. If black holes could destroy information, what other physical processes might do the same? Could information destruction occur in other extreme environments, such as the early moments of the Big Bang or the centers of neutron stars? Some physicists began to question whether information conservation was as fundamental as previously believed. Perhaps the universe was more wasteful and forgetful than anyone had imagined. Maybe reality itself had a kind of cosmic amnesia, constantly erasing parts of its own history. Others doubled down on information conservation, arguing that it was so basic to physical law that any theory violating it must be incorrect. They began searching for mechanisms that would allow information to escape from black holes in ways too subtle for Hawking's original calculation to detect. The stage was set for one of the most profound intellectual battles in the history of physics. On one side stood the elegant mathematics of general relativity and Hawking's seemingly ironclad calculation, showing that information must be destroyed. On the other side stood the fundamental principles of quantum mechanics and the conviction that information conservation was too basic to abandon. The resolution would require insights that went far beyond conventional physics, leading to revolutionary new ideas about the nature of space, time, and reality itself. The black hole information paradox had evolved from a technical problem into an existential crisis for physics, forcing scientists to confront the deepest questions about the universe and our place within it. The battle lines were drawn, and the future of physics hung in the balance. The collision between Hawking's discovery and the foundations of quantum mechanics created more than just an academic disagreement. It threatened to tear apart the entire conceptual framework that physicists had spent centuries building, like discovering that the ground beneath a magnificent cathedral was slowly crumbling away. To understand why the information paradox posed such an existential threat to physics, we need to explore the deep mathematical and philosophical principles that make modern science possible. At its heart, quantum mechanics rests on a mathematical structure called a Hilbert space, an infinite dimensional arena where quantum states live and evolve. Think of it as the ultimate stage where all possible realities can play out simultaneously. Every quantum system, from a single electron to the entire universe, has its complete description encoded as a vector in this abstract mathematical space. The evolution of quantum systems follows the Schrödinger equation, one of the most beautiful and powerful equations in all of physics. This equation tells us how quantum states change over time, much like Newton's laws tell us how classical objects move. But there's a crucial difference. Newton's laws can be irreversible. Balls can roll downhill and dissipate their energy as heat, never to return to their original state spontaneously. The Schrödinger equation, however, is perfectly reversible. Given complete information about a quantum system at any moment, you can calculate its state at any other time, past or future, with perfect accuracy. This reversibility isn't just a mathematical convenience, it's a fundamental requirement for the logical consistency of quantum mechanics. This reversibility is guaranteed by what mathematicians call unitarity, a property that ensures the total probability of finding a system in some state always equals exactly 1. It sounds simple, but this requirement places iron constraints on how quantum systems can evolve. The mathematics demands that information about quantum states can never be created or destroyed, only transformed from one form to another. Imagine the quantum state of a system as a perfectly preserved fossil record. No matter how complex the evolution, no matter how chaotic the interactions, the complete history remains encoded somewhere in the final state. Like a cosmic detective story where every clue is preserved forever, quantum mechanics ensures that the past is never truly erased. only encrypted in increasingly complex ways. This principle connects quantum mechanics to broader philosophical questions about determinism and free will. In classical physics, determinism means that the future is completely determined by present conditions, plus the laws of physics. Quantum mechanics introduces fundamental uncertainty about individual measurement outcomes, but preserves a form of determinism at the level of probability distributions. If you know the quantum state of a system perfectly, you can predict the probabilities of all possible measurement outcomes with absolute precision. The individual results may be random, but the statistical patterns they follow are completely determined. This quantum determinism depends crucially on information conservation. Lose information, and even the probabilities become unpredictable. The threat posed by black holes goes far deeper than just violating quantum mechanics. Information loss would break the logical consistency that makes scientific prediction possible at all. In a universe where information can be destroyed, even perfect knowledge of present conditions wouldn't be enough to predict future behavior, because relevant information might simply vanish without warning. Consider the implications for scientific methodology itself. Science works by assuming that natural phenomena follow consistent laws that can be discovered through observation and experimentation. If black holes can erase information, then they represent processes that are fundamentally unpredictable, immune to scientific understanding, even in principle. This wouldn't just affect exotic phenomena involving black holes. The same mathematical structures that describe black hole formation and evaporation also appear in other areas of physics. If unitarity fails for black holes, it might fail elsewhere too, potentially undermining our understanding of atomic physics, chemistry, condensed matter physics, and every other field that relies on quantum mechanics. The problem becomes even more acute when you consider what physicists call the measurement problem. In quantum mechanics, measurement appears to cause wave function collapse, where a system that existed in multiple states simultaneously suddenly adopts a definite value. This collapse process has always been mysterious, but it preserves information by transferring it from the quantum system to the measuring apparatus plus environment. If black holes can truly destroy information, they would represent something unprecedented in physics, a process that eliminates information without transferring it anywhere else. This would be like having a measuring device that not only fails to record the result of a measurement, but actually erases the fact that the measurement ever took place. The mathematical framework of quantum field theory, which combines quantum mechanics with special relativity, places even stricter constraints on information processing. Quantum field theory describes particles as excitations in underlying fields that permeate all of space and time. The interactions between these fields must satisfy principles like causality and Lorentz invariance that further restrict how information can flow. In quantum field theory, information cannot travel faster than light, and it cannot be created or destroyed at any point in space-time. These requirements ensure that the theory respects both the quantum principle of information conservation and the relativistic principle that cause must precede effect. Black hole information loss would violate both principles simultaneously. The situation becomes even more constrained when you include general relativity, Einstein's theory of gravity. Relativity describes space-time as a dynamic entity that can bend, stretch, and even develop holes like those around black holes. But relativity also demands that the laws of physics look the same to all observers, regardless of their motion or location. This principle, called general covariance, means that information destruction in one reference frame must look like information destruction in all reference frames. You can't save quantum mechanics by claiming that information destruction only appears to occur from certain viewpoints. If information is lost according to any observer, it's lost according to all observers. The conflict between general relativity and quantum mechanics runs even deeper than information conservation. The two theories make fundamentally different assumptions about the nature of space and time. Relativity treats space-time as a smooth, continuous manifold, like a perfectly flexible rubber sheet. Quantum mechanics suggests that space and time might be quantized at the smallest scales, made up of discrete, indivisible units. At the Planck scale, distances of about 10 to the minus 35 meters and times of about 10 to the minus 43 seconds, quantum effects become strong enough to significantly affect the geometry of space-time itself. At these scales, the smooth space-time of general relativity gives way to a foamy, fluctuating structure where the very concepts of distance and duration lose their clear meaning. Black holes force these two theories into direct confrontation in a way that no other known phenomenon does. The event horizon marks a boundary where both quantum effects and gravitational effects become crucial. Neither theory alone is sufficient to understand what happens there, yet combining them leads to apparent contradictions, like the information paradox. Some physicists argue that this contradiction signals the need for a new theory of quantum gravity, one that would unify quantum mechanics and general relativity into a single coherent framework. Such a theory might resolve the information paradox by revealing new physical processes that operate at the intersection of quantum and gravitational phenomena. But developing quantum gravity has proven extraordinarily difficult. The mathematical techniques that work so well for quantum mechanics and general relativity separately seem inadequate for the combined theory. Physicists have pursued multiple approaches, including string theory, loop quantum gravity, causal dynamical triangulation, and many others, but none has achieved complete success. The information paradox serves as a crucial test case for any proposed theory of quantum gravity. Any successful theory must be able to resolve the paradox in a way that preserves the essential insights of both quantum mechanics and general relativity, while making new predictions that can potentially be tested experimentally. Meanwhile, the philosophical implications of the paradox continue to reverberate through physics and beyond. If information can be destroyed, what does this mean for concepts like truth, knowledge, and objective reality? In a universe where facts can be permanently erased, does the concept of absolute truth lose its meaning? Some philosophers argue that information loss would require a fundamental revision of our understanding of physical law. Instead of eternal, unchanging principles, the laws of physics might themselves evolve and change, with black holes serving as cosmic editing rooms where natural law gets rewritten. Others suggest that information loss might be compatible with a more modest view of physical law. Perhaps the laws of physics are not absolute truths, but rather statistical regularities that hold under most circumstances but can be violated in extreme situations. Black holes might represent the universe's way of maintaining overall consistency by occasionally discarding inconvenient information. The debate has also raised questions about the relationship between physical and mathematical reality. Mathematics appears to be timeless and unchanging, with truths like the Pythagorean theorem holding regardless of what happens in the physical world. But if physical processes can destroy information, including potentially mathematical information encoded in physical systems, what does this say about the relationship between mathematical and physical truth? Some mathematicians and physicists have suggested that the information paradox might force us to consider whether mathematical truths themselves could be subject to physical processes. Could a black hole, in principle, destroy not just information about the square root of 2, but somehow affect the mathematical reality of irrational numbers themselves? These questions push far beyond traditional physics into territory that philosophers, mathematicians, and theologians have debated for millennia. The information paradox forces scientists to confront fundamental questions about the nature of existence, knowledge, and reality that they typically prefer to leave to others. At the same time, the practical implications of resolving the paradox could be enormous. Understanding how information behaves in extreme gravitational fields might lead to new technologies for information processing and communication. It might reveal new sources of energy or new ways to manipulate space-time itself. The paradox has already inspired new mathematical techniques and computational methods that have found applications far beyond black hole physics. The debate has pushed physicists to develop new ways of thinking about information, entropy, and the relationship between geometry and quantum mechanics that have proven useful in many other contexts. As the debate continues, it serves as a reminder of how much we still don't understand about the universe we inhabit. The information paradox represents more than just a technical problem in theoretical physics. It's a window into the deepest mysteries of existence, a puzzle that forces us to question our most basic assumptions about reality itself. The resolution of the paradox, whatever form it ultimately takes, will likely require insights that go far beyond our current understanding. It may demand new mathematical techniques, new physical principles, or even new ways of thinking about the relationship between mind and matter, information and reality, knowledge and existence. In the meantime, the paradox stands as one of the great challenges of modern physics, a problem that has already transformed our understanding of black holes, quantum mechanics, and the nature of information itself. Whether it ultimately leads to revolutionary new physics, or to a deeper understanding of existing theories, the black hole information paradox continues to push the boundaries of human knowledge and challenge our understanding of the cosmos we call home. Faced with the existential crisis that the information paradox posed to physics, theorists around the world began crafting solutions with the desperation of architects trying to shore up a collapsing building. Each proposal represented a different philosophical approach to the fundamental question of what happens to information in black holes, and each carried profound implications for our understanding of reality itself. The first and most radical solution came from Stephen Hawking himself. In a move that shocked even his closest colleagues, Hawking embraced what seemed unthinkable to most physicists. Information, he declared, was indeed destroyed by black holes. This wasn't a failure of current theory or a sign that more sophisticated calculations were needed. It was simply how the universe worked. Hawking's position was philosophically bold and mathematically clean. Black holes represented a new kind of physical process, fundamentally different from anything previously encountered in physics. Just as the discovery of radioactivity had revealed that atomic nuclei weren't permanent, and the expansion of the universe had shown that space-time itself could change, black holes demonstrated that information conservation wasn't the absolute principle physicists had believed it to be. This view required abandoning the mathematical structure of unitarity that had been central to quantum mechanics since its inception in the 1920s. Instead of the perfectly reversible evolution described by the Schrödinger equation, quantum mechanics would need to be modified to allow for irreversible information destruction in extreme circumstances. Hawking proposed that the fundamental equations of quantum mechanics should be replaced with more general evolution equations that allowed for information loss. These new equations would reduce to the familiar unitary evolution in ordinary circumstances, but would permit information destruction in the presence of event horizons and other exotic space-time geometries. The implications were staggering. In Hawking's modified quantum mechanics, the universe would become fundamentally unpredictable in a new way. Even perfect knowledge of present conditions wouldn't be enough to determine future probabilities if black holes could arbitrarily erase relevant information. The cosmos would possess a kind of cosmic forgetfulness, constantly editing its own history. This proposal attracted support from physicists who valued general relativity above quantum mechanics. If one theory had to give way, they argued, perhaps it should be quantum mechanics. After all, general relativity had made dramatic predictions about the large-scale structure of the universe that had been confirmed by observation, from the expansion of space to the existence of gravitational waves. But the majority of physicists found information destruction too high a price to pay. Quantum mechanics wasn't just one theory among many, it was the foundation upon which almost all of modern physics was built. Abandoning information conservation would require rebuilding chemistry, atomic physics, condensed matter physics, and countless other fields from scratch. The second major approach took the opposite philosophical stance. Information couldn't be destroyed, these physicists argued, because the mathematical foundations of quantum mechanics were simply too solid to abandon. If Hawking's calculations suggested information loss, then the calculation must be missing something crucial. Gerard 't Hooft, a Dutch physicist who had won the Nobel Prize for his work on the fundamental forces of nature, became a leading proponent of this view. 't Hooft argued that information falling into a black hole must somehow be encoded on the event horizon itself, rather than disappearing into the interior where it could never be recovered. This idea, which would later evolve into the holographic principle, suggested that the three-dimensional volume inside a black hole was somehow equivalent to information stored on its two-dimensional surface. It was as if the event horizon acted like a cosmic hard drive, storing perfect records of everything that had ever fallen in. The mathematics behind this proposal were initially sketchy, but the philosophical motivation was compelling. If information could never be destroyed, then it must be preserved somewhere. The event horizon was the last place where outside observers could potentially access information about infalling matter, so it made sense that the information would be encoded there. 't Hooft's approach required imagining space-time in radically new ways. Instead of thinking of black holes as empty regions surrounded by event horizons, you had to picture them as information processing systems where three-dimensional reality emerged from two-dimensional data storage. It was like discovering that what appeared to be a solid object was actually a sophisticated hologram. This holographic picture raised profound questions about the nature of space itself. If the interior of a black hole could be completely described by information on its surface, what did that say about the reality of the interior volume? Was three-dimensional space itself somehow illusory, an emergent phenomenon arising from more fundamental two-dimensional information? A third approach focused on the mechanism of information retrieval rather than its storage. Leonard Susskind, the Stanford physicist, who had emerged as one of Hawking's most vocal critics, proposed that information could escape from black holes through subtle correlations in the Hawking radiation itself. Susskind's idea was that Hawking radiation wasn't perfectly thermal after all. While individual photons leaving the black hole might appear random, there could be incredibly subtle correlations between different particles that encoded information about the black hole's contents. These correlations would be so weak and so complex that they would be virtually impossible to detect with any conceivable technology, but they would be there in principle. This proposal required imagining that black holes were vastly more complex information processing systems than Hawking had calculated. Instead of simply evaporating through thermal emission, black holes would need to perform incredibly sophisticated quantum computations to encode information about their contents into the outgoing radiation. The computational requirements were mind-boggling. A black hole would need to keep track of every quantum degree of freedom of every particle that had ever fallen in, then gradually encode this information into subtle correlations in particles that might not be emitted until billions of years later. It would be like expecting a furnace to encode the complete works of Shakespeare into the random motion of smoke particles. Yet Susskind argued that quantum mechanics demanded exactly this kind of complex behavior. Information conservation wasn't just a nice mathematical property, it was a fundamental requirement that physics had to satisfy, regardless of how complicated the mechanisms became. A fourth approach suggested that information might indeed be lost from the perspective of outside observers. but preserved in a different form that couldn't interact with the external universe. This was the remnant scenario, proposed by several physicists, including William Unruh and others. The idea was that black hole evaporation might not be complete. Instead of disappearing entirely, black holes might shrink down to some minimum size determined by quantum gravity effects at the Planck scale. These remnants would be incredibly tiny, far smaller than atomic nuclei, but they would contain all the information that had ever fallen into the original black hole. These remnants would be invisible to ordinary matter and energy, interacting so weakly with the outside world that they would be essentially undetectable. From the perspective of outside observers, the information would appear to be lost, but it would actually be stored in these microscopic remnants, preserving the principle of information conservation in a technically correct but practically meaningless way. The remnant scenario faced serious theoretical problems. If information was stored in Planck-scale objects, then these remnants would need to have enormous internal complexity despite their tiny size. They would be like cosmic libraries, compressed to smaller than the period at the end of this sentence, containing more information than could fit in any ordinary volume of space. Moreover, if such remnants existed and were stable, they would be produced not just by black hole evaporation, but by any high-energy process that created virtual black holes. This would lead to the creation of vast numbers of remnants throughout the universe, potentially affecting the behavior of ordinary matter in observable ways. A fifth approach questioned whether the information paradox was real at all. Some physicists argued that the problem arose from applying quantum mechanics in situations where it might not be valid. The extreme conditions near black hole event horizons might require new physics that went beyond both quantum mechanics and general relativity. These physicists suggested that the information paradox was like asking what happens when an irresistible force meets an immovable object. The question assumes that both the irresistible force and the immovable object can exist, but perhaps the real answer is that the assumptions built into the question are flawed. Maybe information conservation and black hole formation were simply incompatible, not because one principle was wrong, but because the combination of conditions needed for both was impossible in nature. Black holes might be prevented from forming by quantum effects that kicked in just before the event horizon could establish itself. This approach required imagining that the classical picture of black hole formation was incomplete. Perhaps the gravitational collapse of massive stars was halted, just short of creating true event horizons, by quantum mechanical effects that became important only in these extreme conditions. Yet another proposal suggested that the information paradox reflected a deeper problem with how physicists thought about time and causality. Some theorists proposed that time itself might not be fundamental, but rather an emergent property of more basic informational processes. In this view, the information paradox arose because physicists were trying to apply concepts like before and after in situations where these concepts lost their meaning. If time emerged from information processing, then the destruction of information might not violate causality, but rather represent a breakdown in the conditions that made temporal concepts meaningful. These early proposals represented more than just technical solutions to a mathematical problem. They were competing visions of the fundamental nature of reality, each implying radically different pictures of space, time, information, and physical law. The debate over these proposals revealed deep philosophical divisions within the physics community. Some physicists were willing to abandon quantum mechanics to preserve general relativity, while others insisted that quantum principles were too fundamental to sacrifice. Some embraced radical new ideas about the nature of space and time, while others preferred to modify existing theories in minimal ways. Each proposal also carried different implications for the broader understanding of physics. If Hawking was right about information destruction, it would require developing entirely new forms of quantum mechanics, If 't Hooft was correct about holographic information storage, it would revolutionize understanding of space-time geometry. If Susskind's correlations were real, it would reveal black holes to be impossibly sophisticated quantum computers. The remnant scenarios raised questions about the fundamental limits of information storage and the nature of space at the smaller scales. The proposals that questioned the reality of the paradox challenged basic assumptions about how physical theories should be applied in extreme conditions. As the debate intensified throughout the 1980s and 90s, it became clear that resolving the information paradox would require insights that went far beyond conventional physics. The early proposals had mapped out the possible approaches, but none provided a completely satisfying resolution. The stage was set for even more radical ideas that would challenge fundamental assumptions about the nature of black holes, space-time, and reality itself. The information paradox had evolved from a technical problem into a battleground where the deepest questions about the universe would be fought. By the 1990s, the information paradox had reached a stalemate. The early proposals had identified possible escape routes, but none provided the mathematical precision needed to settle the debate definitively. Physics needed new weapons in its battle against the paradox, and they arrived in the form of revolutionary ideas that would reshape our understanding of space, time, and the fundamental nature of reality itself. The first breakthrough came from string theory, an ambitious attempt to unify all the forces of nature by replacing point particles with tiny vibrating strings. String theorists had been developing their framework since the 1970s, motivated by the dream of finding a theory of quantum gravity that could reconcile the conflicting demands of quantum mechanics and general relativity. In string theory, particles aren't fundamental point objects, but rather different vibrational modes of incredibly small, one-dimensional strings. These strings exist at energy scales so high and distance scales so small that they remain far beyond the reach of any conceivable experiment. Yet string theory promised to resolve the mathematical inconsistencies that plagued attempts to combine quantum mechanics with gravity. Andrew Strominger and Kamran Vafa, working at Harvard University in the mid-1990s, made a crucial discovery that brought string theory to bear on the information paradox. They showed that certain types of black holes in string theory could be constructed explicitly from known string theory ingredients, allowing precise calculations of their properties, including their entropy. The key insight was that these string theory black holes weren't mysterious gravitational objects whose internal structure was hidden behind event horizons. Instead, they were collections of strings and brains, higher dimensional objects that could be analyzed using the established mathematical techniques of string theory. This allowed physicists to peer inside black holes and understand their microscopic structure for the first time. What Strominger and Vafa found was revolutionary. The entropy of their string theory black holes, calculated by counting microscopic string configurations, exactly matched the Bekenstein-Hawking entropy derived from classical general relativity. This was the first time anyone had been able to provide a microscopic explanation for black hole entropy, showing that it arose from genuine quantum mechanical degrees of freedom, rather than being merely an analogy with thermodynamics. Even more importantly, the string theory calculation showed that black holes had enormous numbers of internal quantum states. These weren't hidden behind the event horizon in some inaccessible way. They were perfectly well-defined quantum mechanical configurations that could, in principle, be analyzed and understood. If black holes had detailed internal structure accessible to quantum mechanical analysis, then information falling into them might be preserved in these internal degrees of freedom. The string theory approach suggested that black holes were more like complex quantum mechanical systems, perhaps analogous to highly excited atoms or molecules, rather than the simple classical objects described by general relativity. Just as the temperature of a gas emerges from the statistical mechanics of molecular motion, the properties of black holes might emerge from the statistical behavior of vast numbers of microscopic string configurations. This microscopic picture offered hope for resolving the information paradox. If information falling into a black hole was encoded in its internal string configurations, then the evaporation process might gradually release this information through subtle correlations in the Hawking radiation. The black hole would act like a quantum mechanical system returning to its ground state, emitting radiation that carried information about its previous excitations. However, the string theory approach came with significant limitations. The black holes that Strominger and Vafa could analyze explicitly were highly specialized objects with properties quite different from the astrophysical black holes that form from collapsing stars. These string theory black holes existed in higher dimensional spacetimes and possessed unusual symmetries that made the calculations tractable but potentially unrepresentative of realistic black holes. Moreover, string theory remained highly speculative, with no direct experimental confirmation of its basic assumptions. Critics argued that using string theory to resolve the information paradox was like using one unproven theory to solve problems created by another. The approach might be mathematically elegant, but it wasn't necessarily physically relevant to the real universe. While string theorists were developing their microscopic picture of black holes, other physicists were pursuing the holographic ideas first suggested by Gerard 't Hooft. The holographic principle had grown from a speculative proposal into a comprehensive framework that suggested a radical revision of our understanding of space and dimensionality. The key insight behind holography was that all the information in a volume of space could be encoded on its boundary surface. This wasn't just true for black holes, but for any region of space-time. Three-dimensional reality might be entirely equivalent to two-dimensional information processing occurring on distant surfaces. This idea received dramatic confirmation in 1997 when Juan Maldacena, then a graduate student at Princeton, discovered a precise mathematical correspondence between gravity theories in curved spacetime and quantum field theories, without gravity living on the boundary of that spacetime. The correspondence, known as ADS-CFT duality, provided the first concrete realization of holographic principles. ADS-CFT duality, where ADS stands for anti-de Sitter space, and CFT for conformal field theory, established that certain gravitational theories, including those containing black holes, were mathematically equivalent to quantum mechanical theories defined on lower dimensional surfaces. It was as if the entire three-dimensional physics of black hole formation and evaporation was encoded in a two-dimensional quantum mechanical system living on a distant boundary. This correspondence wasn't just an analogy or approximation, it was a precise mathematical equivalence. Every question about black hole physics in the gravitational theory could be translated into a question about the boundary quantum field theory, where the familiar rules of quantum mechanics applied without modification. In the boundary theory, there were no black holes, no event horizons, and no information paradox. Information evolution was perfectly unitary, following the standard rules of quantum mechanics. If information appeared to be lost in the gravitational description, it was because physicists weren't looking at the problem from the right perspective. The information was always there in the boundary theory, waiting to be decoded. The ADS-CFT correspondence provided the strongest evidence yet that information was conserved in black hole evaporation, but it did so at the cost of radically revising our understanding of space-time. If three-dimensional gravity was equivalent to two-dimensional quantum mechanics, then the three-dimensional space-time we thought we inhabited might be a kind of illusion, an emergent approximation to more fundamental two-dimensional information processing. The holographic principle suggested that black hole interiors weren't physically real in the way physicists had assumed. Instead, they were computational constructs that emerged from quantum entanglement and information processing on the boundary. The volume inside a black hole might be as illusory as the depth in a holographic image, a three-dimensional appearance created by two-dimensional reality. This holographic resolution of the information paradox was intellectually satisfying but conceptually challenging. If space-time itself was emergent from quantum information processing, then the familiar notions of space and time that humans use to navigate the world were approximate concepts that broke down in extreme conditions. Just as the development of holographic ideas was providing new hope for resolving the information paradox, a new challenge emerged that threatened to make the situation even worse. In 2012, Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, working at the University of California, Santa Barbara, discovered what became known as the firewall paradox. The AMPS collaboration, as the four physicists became known, started with the assumption that information was indeed conserved in black hole evaporation, as suggested by string theory and holographic arguments. They asked what this conservation would imply for the experience of an observer falling through a black hole's event horizon. Classical general relativity predicted that such an observer would experience nothing unusual at the event horizon itself. The horizon would appear as empty space, and the observer would fall smoothly toward the singularity, experiencing increasingly strong tidal forces, but no sudden disruption at the boundary. But AMPS showed that information conservation demanded something radically different. If information was being released in the Hawking radiation, then the quantum state of particles just outside the event horizon would need to be correlated with both the outgoing radiation and the black hole interior. Quantum mechanics forbids such multiple correlations, creating a logical contradiction. The only way to resolve this contradiction, AMPS argued, was to abandon the assumption that space was smooth near the event horizon. Instead, the boundary of the black hole would need to be a violent, high-energy region that would incinerate any observer trying to cross it. They called this the firewall paradox, because the event horizon would act like a wall of fire that destroyed anything approaching the black hole. The firewall proposal was shocking because it suggested that either information conservation or the smooth structure of space-time near event horizons had to be abandoned. Both principles seemed fundamental to physics, yet they appeared to be logically incompatible when combined with reasonable assumptions about quantum mechanics. The firewall paradox reignited the information debate with new intensity. If AMPS were correct, then black holes violated either unitarity or the equivalence principle, a cornerstone of general relativity that states that freely falling observers shouldn't detect anything special about their local environment. Some physicists embraced the firewall idea, arguing that it represented a necessary consequence of taking information conservation seriously. Others rejected it as an artifact of oversimplified assumptions about how quantum information could be distributed near black holes. Leonard Susskind, one of the strongest advocates for information conservation, initially fought against the firewall proposal. He argued that the AMPS analysis made unrealistic assumptions about how observers could access information in quantum systems. Real observers had limited computational abilities and couldn't extract the perfect information that the firewall argument required. But as the analysis was refined and strengthened, even Susskind began to waver. The firewall argument seemed mathematically solid within its assumptions. If information conservation was to be preserved, something dramatic had to happen at black hole boundaries. The firewall debate forced physicists to confront uncomfortable questions about the relationship between mathematical consistency and physical reality. Even if information conservation could be maintained mathematically, what did it mean if the cost was replacing the smooth, empty space of general relativity with walls of destructive energy? Some physicists suggested that the firewall paradox indicated that the entire framework of thinking about black holes in terms of classical space-time geometry was wrong. Perhaps black holes weren't regions of curved space-time at all, but rather some completely different type of physical system that only appeared to have geometric properties when viewed from a distance. Others proposed that the paradox arose from trying to describe black holes from the perspective of external observers who could never actually observe the interior. Perhaps the questions that led to firewalls were simply the wrong questions to ask, based on assumptions about space-time that broke down in extreme gravitational environments. The firewall controversy also highlighted deep questions about the nature of locality in quantum mechanics. Classical physics assumes that events at different locations in space can be treated independently, but quantum mechanics allows for non-local correlations that seem to violate this assumption. Black holes pushed these quantum non-local effects to their limit, potentially requiring abandonment of locality itself. As the debate over firewalls intensified, it became clear that the information paradox had evolved far beyond its original formulation. What had started as a question about information conservation had become a comprehensive challenge to the foundations of both quantum mechanics and general relativity. The proposed solutions had become increasingly radical, requiring abandonment of cherished assumptions about space, time, locality, and the nature of physical reality. String theory suggested that black holes were made of microscopic quantum components. Holography implied that space-time itself was emergent from quantum information processing. Firewalls threatened to replace smooth space-time with violent energy barriers. Each approach offered insights, but at the cost of revolutionary changes to fundamental physics. The information paradox had become a crucible that was forcing physics to evolve or break under the strain of its own contradictions. Yet despite decades of intense effort by some of the most brilliant minds in physics, no consensus had emerged. The paradox remained as puzzling and controversial as ever, serving as a constant reminder of how much remained unknown about the deepest laws governing reality. The battle over black hole information had revealed that our understanding of the universe was far more fragile and incomplete than anyone had imagined. The search for resolution continued to drive physics into uncharted territory, where the familiar concepts of space and time might themselves need to be replaced by something entirely new and unfamiliar. In the midst of the escalating theoretical battles over firewalls and holography, a quiet physicist at the University of Alberta had been working on a different approach to the information paradox. Don Page, a former student and collaborator of Stephen Hawking, had spent years thinking about the quantum mechanics of black hole evaporation with a precision and mathematical rigor that would eventually prove prophetic. Page's insight came from thinking carefully about what information conservation would actually require during the process of black hole evaporation. If information was truly conserved, then the total entropy of the black hole, plus its radiation, would have to remain constant throughout the evaporation process. But this simple requirement led to a surprising and counterintuitive prediction about how information should flow out of evaporating black holes. In 1993, Page calculated what the entropy of Hawking radiation should look like if information was perfectly conserved. Initially, as the black hole began to evaporate, the radiation would indeed appear thermal and random, carrying no information about the black hole's contents. The entropy of the radiation would steadily increase as more thermal photons and particles streamed away from the black hole. But Page showed that this behavior couldn't continue indefinitely. At some critical point, roughly when the black hole had evaporated away half of its original mass, something dramatic would have to change. The entropy of the Hawking radiation would have to stop increasing and begin to decrease, even though the black hole continued to emit particles at an accelerating rate. This transition point, which became known as the Page time, represented the moment when information would finally begin to escape from the black hole in earnest. After the Page time, the Hawking radiation would gradually transition from appearing thermal and random to carrying detailed information about everything that had ever fallen into the black hole. The curve that Page calculated, showing entropy first rising and then falling, became known as the Page curve. It looked like an inverted V, rising to a peak at the page time, and then declining back to zero when the black hole finally evaporated completely. This curve became the gold standard for any proposed resolution of the information paradox. Any successful theory would have to reproduce Page's curve exactly. The physical picture behind the Page curve was both elegant and strange. During the first half of the evaporation process, information about infalling matter would be stored inside the black hole, inaccessible to outside observers. The Hawking radiation during this period would appear thermal because it carried no information about the black hole's detailed internal state. But as the black hole continued to shrink, something remarkable would happen. The information stored inside would begin to affect the properties of newly emitted radiation through subtle quantum mechanical correlations. These correlations would be incredibly weak and complex, far too subtle to detect with any practical measurement, but they would be there in principle. After the Page time, the situation would reverse entirely. The Hawking radiation would carry more information about the black hole's contents than remained inside the black hole itself. The evaporation process would become like playing a movie in reverse, with later radiation carrying detailed information about what had fallen in earlier. Page's calculation was based on pure quantum mechanical principles, without reference to specific theories of quantum gravity or detailed models of black hole interior structure. It simply asked what would have to be true if information conservation held, regardless of the underlying physical mechanisms. This model-independent approach gave Page's results special significance in the debates over the information paradox. Any proposed resolution would ultimately have to reproduce the Page curve, regardless of whether it relied on string theory, holographic principles, or entirely different physical ideas. However, Page's calculation also highlighted just how strange the required information transfer would be. The correlations that would allow information to escape after the Page time would involve quantum entanglement between particles separated by vast distances and enormous time intervals. Early Hawking radiation would somehow need to be correlated with particles that wouldn't be emitted until billions of years later. These correlations would require the black hole to perform incredibly sophisticated quantum computations, keeping track of every detail of its internal state, while encoding this information into subtle patterns in the outgoing radiation. The computational requirements seem to far exceed anything that could be accomplished by known physical processes. Page's work remained largely theoretical for decades, because no one could demonstrate that the required correlations could actually arise in realistic models of black hole evaporation. The mathematics of quantum field theory in curved space-time was simply too complex to calculate the detailed behavior of Hawking radiation throughout the entire evaporation process. But this situation began to change dramatically in the 2010s as physicists developed new mathematical techniques inspired by the ADS-CFT correspondence. These techniques allowed precise calculations of information flow in quantum systems that were too complex to analyze with traditional methods. The breakthrough came from understanding that the holographic correspondence wasn't just a theoretical curiosity, but a practical calculational tool. Questions about information flow in gravitational theories could be translated into equivalent questions about quantum entanglement in boundary field theories, where established quantum mechanical techniques could provide precise answers. Netta Engelhardt and Aaron Wall, working independently, developed new mathematical techniques called quantum extremal surfaces that allowed calculation of entanglement entropy in holographic theories with unprecedented precision. These techniques could track the flow of quantum information throughout complex gravitational processes, including black hole formation and evaporation. Using these new tools, physicists began to reproduce Page's curve from first principles for the first time. In 2019, Jeff Pennington, working at Stanford, made a crucial breakthrough by showing that the Page curve emerged naturally from holographic calculations once quantum corrections to classical geometry were properly included. Pennington's calculation revealed that the classical picture of black hole geometry, where information fell past the event horizon and disappeared into the interior, was incomplete. Quantum mechanical effects would modify the geometry in subtle ways that allowed information to escape through quantum tunneling and other quantum mechanical processes. The key insight was that quantum mechanics didn't just affect the matter falling into black holes, it affected the space-time geometry itself. The smooth classical picture of event horizons and black hole interiors was an approximation that broke down when quantum effects were included with sufficient precision. Ahmed Almheri, Netta Engelhardt, Don Maroff, and Henry Maxfield extended these results by showing how quantum error correction, a concept borrowed from quantum computing research, could explain how information was preserved and eventually retrieved during black hole evaporation. In quantum error correction, information is stored in quantum systems in ways that are robust against noise and decoherence. Even if parts of the system are lost or corrupted, the information can be recovered from the remaining components. Black holes, they suggested, might be natural quantum error, correcting systems that protected information from destruction, even in extreme gravitational environments. This error correction picture provided a detailed mechanism for how the page curve could emerge. Information falling into a black hole would be encoded redundantly across many quantum degrees of freedom, both inside the black hole and in the early Hawking radiation. This redundancy would ensure that the information could be recovered from the late-time radiation, even after the black hole interior was no longer accessible. The quantum error correction approach also provided new insights into the firewall paradox. The apparent contradiction between smooth horizons and information conservation arose from assuming that information had to be stored in specific locations in space-time. But quantum error correction showed that information could be stored non-locally, distributed across regions that appeared disconnected in classical geometry. From this perspective, the firewall paradox was based on a false dichotomy. Information could be preserved without requiring violent energy densities at event horizons because the information wasn't localized there in the first place. The smooth horizon and information conservation were both approximate concepts that emerged from more fundamental quantum mechanical processes. These developments were supported by breakthrough calculations in simplified models of black hole evaporation. Physicists studying two-dimensional models of gravity, where the mathematics was tractable enough to allow exact solutions, found clear evidence for page curve behavior and information conservation. While these toy models were far simpler than realistic four-dimensional black holes, they provided crucial proof of principle that information conservation was compatible with black hole evaporation. The models showed explicitly how information could flow out of black holes through quantum mechanical channels that were invisible in classical general relativity. Daniel Harlow and Patrick Hayden made another crucial contribution by connecting the information paradox to concepts from quantum complexity theory. They showed that the computational difficulty of extracting information from Hawking radiation was related to fundamental limits on how quickly quantum information could be processed and transferred. Their work suggested that information might be preserved in black hole evaporation, but in forms that were computationally inaccessible to any realistic observer. The information would be there in principle, satisfying the requirements of unitarity, but scrambled so thoroughly that extracting it would require computational resources far exceeding anything available in the universe. This computational perspective provided a new way of thinking about the apparent tension between information conservation and practical inaccessibility. Information could be perfectly conserved from a fundamental physics perspective, while being effectively lost from any practical standpoint. The emergence of the page curve in rigorous calculations marked a turning point in the information paradox debates. For the first time, physicists could show explicitly how information conservation worked in models that captured the essential features of black hole evaporation. But these advances also raise new questions about the nature of space-time and reality. If the page curve was correct, then the classical picture of smooth space-time with sharply defined event horizons was fundamentally wrong. Reality at the quantum level was far stranger and more interconnected than classical physics suggested. The quantum mechanical processes that allowed information to escape from black holes involved correlations and entanglements that spanned enormous distances and timescales. Particles emitted early in the evaporation process would be quantum mechanically connected to particles emitted billions of years later in ways that had no classical analog. These quantum connections suggested that space-time itself might be woven together by information and entanglement in ways that physicists were only beginning to understand. The familiar three-dimensional space and one-dimensional time of everyday experience might be emergent phenomena arising from more fundamental quantum information processing. The success of page curve calculations also validated the holographic approach to gravity and quantum mechanics. The correspondence between gravitational theories and quantum field theories wasn't just a mathematical curiosity, but a fundamental feature of how nature worked at the deepest level. Yet significant challenges remained. The calculations that reproduced the page curve relied on simplified models and approximations that might not capture all the complexities of realistic black holes. The transition from toy models to fully realistic black holes remained a formidable mathematical challenge. Moreover, the page curve calculations didn't resolve all the conceptual puzzles raised by the information paradox. They showed that information could be conserved in principle, but they didn't explain what it would mean for an observer falling into a black hole during the page-time transition. The quantum mechanical processes that allowed information to escape also raised questions about the causal structure of space-time. If information could flow through quantum channels that bypassed classical space-time geometry, what did this mean for concepts like locality and causality that were central to our understanding of physics? Despite these remaining challenges, the emergence of the page curve marked a decisive shift in how physicists thought about the information paradox. The question was no longer whether information could be conserved, but rather how the conservation worked and what it implied for our understanding of space-time and quantum mechanics. The paradox had evolved from an existential threat to physics into a window for discovering new principles that connected quantum mechanics, gravity, and information in previously unimaginable ways. The resolution was emerging not through abandoning cherished principles, but through discovering how those principles work together at a deeper level than anyone had previously understood. For decades, the information paradox remained trapped in the realm of pure theory, a battle fought with mathematics and thought experiments far removed from the messy reality of actual observations. Black holes seemed to guard their secrets jealously, hiding behind event horizons that no telescope could penetrate, and emitting Hawking radiation so faint that detecting it appeared hopeless. But the 21st century brought a revolution in observational astronomy that would finally allow humanity to peer into the cosmic abyss and search for clues about the ultimate fate of information. The first breakthrough came not from looking at black holes directly, but from detecting the ripples they created in the fabric of space-time itself. On September 14th, 2015, at exactly 9:51 Coordinated Universal Time, two identical detectors separated by 3,000 kilometers simultaneously recorded a signal that had been traveling toward Earth for over 1 billion years. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, had detected gravitational waves for the first time in human history. These waves were the dying screams of two black holes, each about 30 times more massive than our Sun, as they spiraled into each other and merged in a cataclysmic collision that released more energy in gravitational waves than all the stars in the observable universe emit in light. The detection was a triumph for Einstein's theory of general relativity, confirming a prediction he had made exactly 100 years earlier. But for physicists studying the information paradox, the gravitational wave signal offered something even more valuable than theoretical vindication. It provided the first direct observational data about black hole dynamics and behavior. The LIGO signal, designated GW150914 after its discovery date, revealed precise details about the masses, spins, and orbital characteristics of the merging black holes. As the two objects spiraled closer together, their gravitational interaction accelerated them to significant fractions of the speed of light. The final merger happened in less than 0.2 of a second, creating a new black hole with a mass slightly less than the sum of its components. This missing mass, about 3 times the mass of our Sun, had been converted entirely into gravitational wave energy, according to Einstein's famous equation. The conversion was so efficient that for a brief moment, the merger outshone all the stars in the observable universe, not in light, but in gravitational radiation. For information paradox researchers, the most intriguing aspect of the signal was what it revealed about the final, merged black hole. The gravitational waves showed that the new black hole was spinning rapidly and had settled into a stable configuration within milliseconds of the merger. This rapid stabilization suggested that black holes were indeed simple objects, characterized completely by their mass, spin, and electric charge, just as classical general relativity predicted. But this simplicity raised profound questions about information. If two complex black holes, each potentially containing the scrambled information of billions of years of stellar evolution, could merge to form a simple spinning black hole with no memory of its components' detailed histories, where did all that information go? The gravitational wave observations showed that the merger process was violent and chaotic, with the black hole's event horizons stretching and deforming in complex ways before settling into a smooth, spherical shape. During this brief period of chaos, enormous amounts of energy were released in gravitational waves that carried detailed information about the dynamics of the merger. Some physicists speculated that these gravitational waves might carry subtle information about the internal states of the merging black holes, encoded in patterns too complex for current technology to decipher. The waves contained thousands of oscillation modes and frequency components that might, in principle, encode information about everything that had ever fallen into either black hole. But extracting such information would require measurement precision far beyond current capabilities. The gravitational wave detectors were sensitive enough to measure distortions smaller than 1/10,000th the width of a proton, yet even this extraordinary precision was insufficient to detect the subtle correlations that might encode information about black hole contents. Following the initial detection, LIGO and its European counterpart Virgo detected dozens of additional black hole mergers, each providing new data about black hole behavior. Some mergers involved black holes with very different masses. Others featured rapidly spinning objects, and a few showed evidence of precession and other complex orbital dynamics. Each detection refined understanding of how black holes behave in extreme conditions, but none provided clear evidence for or against information conservation. The gravitational waves carried tremendous amounts of information about the merger dynamics, but this information seemed to be entirely geometric, describing the motion and deformation of space-time rather than the quantum mechanical contents of the black holes themselves. Perhaps more significant was what the gravitational wave observations revealed about the stability and predictability of black hole behavior. Every merger followed the precise mathematical predictions of general relativity with extraordinary accuracy. Black holes behaved exactly like the simple geometric objects Einstein had envisioned, showing no signs of the complex internal structure that information conservation seemed to require. While gravitational wave detectors were revolutionizing the study of black hole dynamics, another technological breakthrough was preparing to image black holes directly for the first time. The Event Horizon Telescope, or EHT, represented one of the most ambitious observational projects in the history of astronomy, linking radio telescopes around the world to create a virtual telescope as large as Earth itself. The EHT targeted two supermassive black holes that offered the best chances for direct imaging. Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy, appeared relatively large in the sky despite being 26,000 light-years away. But atmospheric turbulence and variable emission from the galactic center made it a challenging target. The second target was far more distant but offered better observing conditions. Messier 87, a giant elliptical galaxy 55 million light-years away, contained a black hole with a mass of 6.5 billion times that of our Sun. This monster was large enough and steady enough to serve as an ideal target for humanity's first attempt at black hole photography. On April 10, 2019, the EHT collaboration announced they had successfully imaged the black hole in Messier 87. The image showed exactly what Einstein's theory predicted: a bright ring of emission surrounding a dark central region. The dark area represented the black hole's shadow, the region from which no light could escape to reach Earth. The image was both thrilling and frustrating for information paradox researchers. It confirmed that black holes possessed event horizons and cast shadows, just as general relativity predicted. The boundary between the bright emission region and the dark shadow was sharp and well defined, showing no signs of the fuzzy or irregular structure that some quantum theories of gravity had suggested. But the image also revealed tantalizing hints of complexity. The emission ring wasn't perfectly symmetric, showing bright spots and asymmetries that reflected the complex dynamics of matter swirling around the black hole. This matter, heated to billions of degrees as it fell toward the event horizon, emitted intense radiation that carried information about magnetic fields, rotation rates, and other properties of the accretion flow. The EHT observations showed that matter approaching the event horizon behaved in complex and sometimes unpredictable ways. Magnetic field lines twisted and reconnected, creating jets of plasma that shot away from the black hole at nearly the speed of light. These jets carried enormous amounts of energy and momentum, but whether they carried information about the black hole's internal state remained unclear. The precision of the EHT measurements allowed detailed tests of general relativity in the strong gravity regime near the event horizon. Every observation matched Einstein's predictions with remarkable accuracy, providing no evidence for the modifications to space-time geometry that some approaches to the information paradox required. Yet the observations also revealed just how dynamic and complex the environment around black holes could be. The accretion disk surrounding Messier 87's black hole contained more mass than our entire solar system, all compressed into a region smaller than our solar system's diameter. The energy densities and magnetic field strengths in this environment approached theoretical limits, creating conditions unlike anything else in the known universe. Some physicists wondered whether these extreme conditions might provide natural laboratories for testing theories of quantum gravity and information conservation. The interactions between infalling matter and intense gravitational fields might produce observable signatures of the quantum mechanical processes that preserved or destroyed information. But detecting such signatures would require observational capabilities far beyond current technology. The quantum mechanical effects that might resolve the information paradox operated on scales trillions of times smaller than anything the EHT could resolve. Even future improvements in telescope technology seemed unlikely to bridge this enormous gap between theory and observation. The EHT also imaged Sagittarius A star, the black hole at the center of our own galaxy. This image, released in 2022, showed a similar ring structure, but with more variability and complex dynamics. The closer proximity allowed more detailed observations of the matter flow patterns and emission characteristics around the event horizon. Both EHT targets showed evidence of rotation, with matter swirling around the black holes in complex patterns that carried angular momentum toward the event horizon. This rotation had important implications for information storage, as spinning black holes could potentially store more information than their non-rotating counterparts. The observations also revealed that black holes were incredibly efficient at converting infalling matter into energy. The accretion processes around both targets released more energy per unit mass than nuclear fusion, making black holes among the most efficient energy conversion mechanisms known to physics. But this efficiency raised new questions about information conservation. If black holes could convert matter into energy with such remarkable efficiency, what happened to the quantum information encoded in the original matter? Did it get transferred to the emitted radiation, stored in the black hole's internal degrees of freedom, or genuinely destroyed? The observational data provided constraints on theoretical models, but couldn't definitively answer these questions. The energy and information flows around black holes operated on scales and timescales that remained beyond direct observational reach. Meanwhile, other astronomical observations were providing indirect clues about black hole behavior over cosmic timescales. Surveys of quasars and active galactic nuclei showed that supermassive black holes had grown from relatively small seeds in the early universe to the giants observed today. This growth required the accretion of enormous amounts of matter and energy over billions of years. The consistency of quasar properties across cosmic time suggested that black holes had remained stable and predictable throughout their growth phases. There was no observational evidence for the complex information processing or quantum mechanical effects that some theories predicted should occur during accretion and growth. X-ray observations from space-based telescopes revealed additional details about matter falling into black holes. The final moments before matter crossed the event horizon were marked by intense emission in high-energy radiation, providing snapshots of the extreme physics operating in the strongest gravitational fields in the universe. These observations showed that matter retained its identity and physical properties right up to the event horizon, emitting characteristic spectral lines and radiation signatures that revealed its composition and physical state. But once matter crossed the boundary, it vanished from observational reach, providing no further clues about its ultimate fate. The accumulation of observational data created a paradoxical situation. Every observation confirmed that black holes behaved exactly as Einstein's classical theory predicted, showing no signs of the quantum mechanical complexity that information conservation seemed to require. Yet the same observations revealed environments of such extreme complexity and energy that quantum effects should be important. This observational evidence couldn't resolve the information paradox, but it provided crucial constraints on proposed solutions. Any successful theory would need to explain why black holes appeared so simple and classical from the outside, while potentially maintaining complex quantum mechanical information processing on the inside. The observations also highlighted the vast scales involved in the information paradox. Black holes operated on timescales of millions or billions of years, size scales ranging from kilometers to light years, and energy scales that spanned dozens of orders of magnitude. Understanding information conservation in such extreme environments required theoretical frameworks that could bridge these enormous ranges. Perhaps most importantly, the observational breakthroughs demonstrated that black holes were not just theoretical constructs, but real, dynamic, observable objects that could be studied with increasingly sophisticated tools. While the deepest questions about information and quantum mechanics remained beyond current observational reach, the rapid pace of technological advancement suggested that future observations might eventually provide more definitive answers. The revolution in black hole observations had transformed the information paradox from a purely theoretical debate into a problem grounded in observational reality. The challenge for physicists was to develop theories sophisticated enough to explain both the elegant simplicity revealed by current observations and the complex quantum mechanical behavior that fundamental physics seem to demand. The black hole information paradox forces us to confront questions that extend far beyond the technical details of quantum mechanics and general relativity. At its deepest level, the paradox challenges our most fundamental assumptions about the nature of existence itself. If information can truly be destroyed, then reality becomes a far stranger and more fragile thing than we had ever imagined, where the very foundation of what we call truth might be subject to cosmic erasure. To understand the full implications of information destruction, we must first grapple with what information means in the context of physical reality. Information is not merely data stored on computer hard drives or words written in books. In the language of physics, information represents the complete specification of reality at its most fundamental level. Every particle's position, every quantum state's superposition, every field's configuration throughout the universe contributes to the total information content of existence. This information forms what we might call the cosmic memory of the universe. Every event that has ever occurred, from the collision of galaxies to the decay of individual atoms, leaves its mark encoded in the quantum mechanical state of the cosmos. The universe remembers its own history not through consciousness or intention, but through the inexorable preservation of information mandated by the laws of quantum mechanics. Consider what this means for our understanding of the past. When we observe ancient light from distant galaxies, we are reading information that has traveled across billions of years of space and time. The photons carry encoded within their quantum states a record of the conditions that existed when they were first emitted. Stars that died billions of years ago continue to exist in the information carried by their light, preserved in the quantum mechanical structure of the electromagnetic field. This cosmic memory extends to every level of physical reality. The atoms in your body carry information about the nuclear furnaces of ancient stars where they were forged. The molecules in your DNA encode information about billions of years of evolutionary history. Even the quantum vacuum that fills empty space seethes with virtual particles that carry information about the fundamental fields and forces that govern reality. In this picture, the past is not gone but transformed, encoded in the present configuration of matter, energy, and quantum fields. The universe is like a vast library where every book ever written continues to exist, though perhaps in forms so scrambled and distributed that reading them requires computational resources beyond imagination. But black holes threaten to burn down this cosmic library. If information falling past an event horizon is genuinely destroyed, then the universe can suffer from a kind of cosmic amnesia, permanently forgetting parts of its own history. The implications are staggering, not just for physics, but for any attempt to understand the meaning and significance of existence itself. Consider what information destruction would mean for the concept of truth. In a universe where information is conserved, every statement about physical reality has a definite truth value, even if we lack the computational resources to determine what that value is. The statement "Shakespeare wrote Hamlet" is either true or false based on historical facts, and those facts are encoded somewhere in the information structure of the universe, even if accessing them is practically impossible. But in a universe where information can be destroyed, the concept of absolute truth becomes problematic. If the information that would establish the truth or falsity of a statement has been erased from existence, then the statement loses its definite truth value. It becomes neither true nor false, but simply meaningless, referring to facts that no longer exist in any sense. This dissolution of truth extends beyond historical questions to the very foundations of physical law. The laws of physics are meaningful only insofar as they make predictions about the behavior of physical systems based on their current states. But if information about those states can be destroyed, then even perfect knowledge of physical law becomes insufficient to predict the future. The destruction of information also undermines the concept of causality in profound ways. Causality relies on the idea that present events are connected to past events through chains of influence that can, in principle, be traced and understood. But if information about past events can be erased, then these causal chains are broken, leaving present events disconnected from their origins. This breakdown of causality doesn't just affect our ability to understand the universe, it calls into question whether the universe itself has any coherent structure. Without reliable causal connections, the cosmos becomes a collection of disconnected events with no underlying logic or pattern. The elegant mathematical laws that seem to govern reality might be nothing more than temporary approximations that break down whenever information is destroyed. The philosophical implications become even more disturbing when we consider the role of consciousness and observation in quantum mechanics. Some interpretations of quantum theory suggest that conscious observation plays a fundamental role in determining the outcomes of quantum measurements. If this is true, then consciousness itself might be threatened by information destruction. Consider what happens when conscious beings fall into black holes. If information is destroyed, then not only do their physical bodies disappear, but the information that constituted their memories, thoughts, and experiences vanishes as well. From the perspective of the outside universe, these beings don't just die, they are retroactively erased from existence, as if they had never lived at all. This erasure extends beyond individual consciousness to the collective memory of civilizations and species. If a technologically advanced civilization fell into a black hole, all of their discoveries, their art, their accumulated knowledge would be lost forever. The universe would forget not just that they existed, but everything they had learned about the nature of reality itself. Even more troubling is the possibility that information destruction could affect the logical structure of mathematics itself. Mathematics appears to exist independently of physical reality, with truths like the Pythagorean theorem holding regardless of what happens in the material world. But some physicists have suggested that mathematical information encoded in physical systems could potentially be destroyed by black holes. If this is possible, then black holes might represent a threat not just to physical reality, but to logical reality as well. The destruction of mathematical information could create logical contradictions or inconsistencies that would undermine the rational structure upon which all human knowledge depends. These concerns might seem abstract and philosophical, but they have concrete implications for how we understand the significance of existence itself. If information can be destroyed, then every moment of conscious experience becomes precious in a new and urgent way. The thoughts you are thinking right now, the experiences you are having, the memories you cherish, might all be subject to cosmic erasure. This gives the information paradox a moral and existential weight that extends far beyond technical physics. The question of whether information is conserved becomes a question about whether existence has permanent meaning, or whether consciousness and experience are ultimately ephemeral phenomena that can be erased without trace. Some philosophers have argued that information destruction might actually be liberating, freeing the universe from the burden of carrying infinite baggage from the past. In this view, black holes serve as cosmic recycling centers that prevent the universe from becoming cluttered with obsolete information, allowing space for genuinely new experiences and possibilities. But this perspective requires accepting that the past can be genuinely lost, that the experiences of countless beings throughout cosmic history might simply vanish as if they had never occurred. The ethical implications of such loss are staggering, particularly when we consider that the information being destroyed includes not just abstract physical data, but the record of conscious experience and suffering. The debate over information conservation also connects to deep questions about personal identity and the continuity of consciousness. If the information that constitutes your thoughts and memories could be destroyed, what would this mean for your sense of self and personal continuity through time? Some philosophers argue that personal identity is nothing more than the continuity of information patterns in the brain. If this information could be genuinely destroyed rather than just transformed, then personal identity becomes a far more fragile concept than we typically assume. Death would represent not just the cessation of biological function, but the complete erasure of the information patterns that constituted a unique conscious experience. The implications extend to questions about the meaning and purpose of life itself. If consciousness and experience can be permanently destroyed, then the universe becomes a place where nothing ultimately matters, where the most profound thoughts and the most beautiful experiences are ultimately destined for oblivion. This existential weight has motivated some physicists to defend information conservation with an intensity that goes beyond purely scientific considerations. The preservation of information becomes not just a technical requirement of quantum mechanics, but a moral necessity for maintaining the meaningfulness of existence. Leonard Susskind, one of the most vocal advocates for information conservation, has argued that the destruction of information would represent a kind of cosmic genocide, the permanent erasure of the experiences and achievements of countless conscious beings throughout the history of the universe. In this view, defending information conservation becomes a moral imperative as much as a scientific one. But other physicists have embraced information destruction as a natural and perhaps necessary feature of a universe that must balance preservation with renewal. Stephen Hawking himself seemed to find a kind of poetic justice in the idea that information could be destroyed, seeing it as evidence that the universe was not a perfect mechanical system, but something more dynamic and creative. The debate also intersects with religious and spiritual questions about the nature of souls, afterlives, and transcendent meaning. If information is conserved, then in some sense, every conscious being that has ever lived continues to exist in the information structure of the universe, even if in forms too scrambled to constitute conscious experience. This scientific immortality might not provide comfort to those hoping for conscious survival after death, but it does suggest that existence has a kind of permanent significance. Every action, every thought, every moment of experience leaves an indelible mark on the structure of reality that can never be completely erased. But if information can be destroyed, then even this scientific immortality is threatened. The universe becomes a place where existence is genuinely temporary, where even the most profound experiences can be completely forgotten by reality itself. These philosophical implications have driven some physicists to pursue increasingly exotic solutions to the information paradox. The stakes feel too high to accept information destruction, even if it seems to be the most straightforward interpretation of black hole physics. Yet the philosophical weight of the paradox also raises questions about whether scientific truth should be influenced by its implications for meaning and value. Should physicists accept or reject theories based on their consequences for human significance? Or should they follow the mathematics regardless of where it leads? This tension between scientific objectivity and human meaning has made the information paradox one of the most emotionally charged debates in modern physics. It's not just a technical disagreement about quantum mechanics and gravity, but a fundamental conflict about the nature and significance of existence itself. The resolution of the paradox, whatever form it ultimately takes, will have implications that extend far beyond physics into philosophy, religion, and our understanding of what it means to be conscious beings in an apparently vast and indifferent universe. If information is conserved, then existence has a kind of permanent reality that transcends individual death and even the heat death of the universe. Every conscious experience becomes part of an eternal cosmic memory that can never be completely lost, even if it can be scrambled beyond recognition. But if information can be destroyed, then we inhabit a universe where forgetting is possible on a cosmic scale. where the most profound achievements of consciousness and civilization can be permanently erased. The choice between these possibilities is not just a matter of physics, but a fundamental question about the kind of universe we live in and our place within it. In confronting the information paradox, we are forced to grapple with the deepest questions about reality, consciousness, and meaning that have puzzled philosophers and theologians for millennia. The answer we ultimately reach will shape not just our understanding of black holes, but our conception of existence itself. As we reach the end of our journey through the labyrinth of black holes and information, we find ourselves standing at the edge of human knowledge, peering into mysteries that may define the next century of physics. The information paradox has evolved from a simple question about what happens when matter falls into black holes into a comprehensive challenge that touches every aspect of our understanding of reality itself. Today, nearly 50 years after Stephen Hawking first proposed that black holes emit radiation, the scientific consensus has shifted decisively toward information conservation. The majority of physicists now believe that information falling into black holes is not destroyed but preserved in ways that our current understanding can only begin to glimpse. This shift represents one of the most dramatic reversals of scientific opinion in modern physics, driven by theoretical breakthroughs that have revealed the deep connections between quantum mechanics, gravity, and information. The evidence for information conservation comes not from direct observation, which remains impossible with current technology, but from the internal consistency of theoretical physics itself. The holographic principle has shown that gravitational theories are mathematically equivalent to quantum mechanical theories without gravity, providing a framework where information conservation is guaranteed by the underlying mathematical structure. The ADS-CFT correspondence has allowed physicists to translate questions about black hole information into questions about quantum entanglement in systems where the familiar rules of quantum mechanics apply without ambiguity. In these holographic theories, information is always conserved, flowing from black hole interiors to the boundary of space-time through quantum channels that have no classical analog. The Page curve has emerged from these holographic calculations with mathematical precision, showing exactly how information should flow out of evaporating black holes. The curve's distinctive shape, rising to a peak and then declining back to zero, has become the gold standard that any complete theory of quantum gravity must reproduce. But this theoretical consensus comes with a profound cost. The preservation of information requires abandoning many of our most cherished intuitions about space, time, and locality. The smooth, empty space of Einstein's general relativity must be replaced by something far stranger and more interconnected, where quantum entanglement weaves space-time together in ways that challenge our basic understanding of geometry. The implications extend far beyond black hole physics. If space and time themselves emerge from quantum information processing, then the familiar three-dimensional world we inhabit is a kind of holographic projection of more fundamental two-dimensional information storage. Reality becomes layered in ways that would have seemed incomprehensible to earlier generations of physicists. Recent developments in quantum error correction have provided new insights into how information might be preserved even in the most extreme gravitational environments. Black holes appear to be natural quantum computers, processing information in ways that protect it from destruction while making it practically inaccessible to outside observers. The information is there, encoded in subtle correlations and quantum entanglements, but extracting it would require computational resources that exceed anything available in the universe. This computational perspective has revealed new connections between physics and computer science that are reshaping both fields. The boundaries between information theory, quantum mechanics, and gravity have begun to dissolve, revealing a more unified picture of physical law where information processing is as fundamental as energy and momentum. Yet significant challenges remain. the holographic theories that successfully reproduce the page curve rely on simplified models that may not capture all the complexity of realistic black holes in our four-dimensional universe. The mathematical techniques that work so elegantly in these toy models become intractably complex when applied to the black holes that actually exist in nature. The firewall paradox continues to haunt attempts at complete resolution. Even if information is conserved in principle, the mechanisms that preserve it seem to require violations of either locality or the smooth structure of space-time near event horizons. The choice between these violations remains unclear, with different approaches to quantum gravity making different predictions about which principles must be sacrificed. Experimental verification remains frustratingly distant. The Hawking radiation from stellar mass black holes is so faint and cold that detecting it directly appears hopeless with any conceivable technology. The quantum mechanical effects that might resolve the information paradox operate on scales that are separated by dozens of orders of magnitude from anything we can observe. The gravitational wave detectors that have revolutionized black hole astronomy provide data about the classical dynamics of black hole mergers, but reveal nothing about the quantum mechanical processes that govern information flow. The Event Horizon Telescope has imaged black hole shadows with unprecedented precision, but these observations probe the classical geometry of space-time rather than the quantum mechanical information processing that might occur near event horizons. This experimental inaccessibility means that progress must continue to rely on theoretical reasoning and mathematical consistency. Physicists find themselves in the unusual position of trying to understand one of nature's most fundamental processes without the guidance of direct experimental data. The search for quantum gravity theories has intensified as physicists recognize that resolving the information paradox requires a complete understanding of how quantum mechanics and gravity combine at the most fundamental level. String theory, loop quantum gravity, causal dynamical triangulation, and dozens of other approaches continue to compete for attention, each offering different insights into the nature of space-time and information. String theory has provided some of the most detailed insights into black hole information processing, showing how the microscopic constituents of black holes might preserve information in their quantum mechanical configurations. But string theory remains highly speculative, with no direct experimental confirmation of its basic assumptions about the fundamental nature of matter and energy. Loop quantum gravity offers a different approach, suggesting that space-time itself is quantized at the smaller scales, made up of discrete building blocks that might prevent the formation of true singularities. But loop quantum gravity has struggled to make contact with the holographic insights that have driven recent progress in black hole information theory. The debate has also revealed deep philosophical divisions within the physics community about the nature of scientific truth and the role of mathematical elegance in understanding reality. Some physicists prioritize internal mathematical consistency, arguing that theories must satisfy certain logical requirements regardless of their experimental accessibility. Others insist that physics must ultimately be grounded in observation and measurement, however indirect. These philosophical differences have shaped approaches to the information paradox in fundamental ways. Physicists who emphasize mathematical consistency have been more willing to accept radical revisions to our understanding of space and time if these revisions preserve the logical structure of quantum mechanics. Those who prioritize observational grounding have been more skeptical of theoretical developments that cannot be tested experimentally. The information paradox has also driven new connections between physics and other fields of human knowledge. Computer scientists working on quantum information theory have provided crucial insights into how quantum mechanical systems can process and store information. Philosophers have contributed to debates about the nature of reality and the meaning of physical existence. Even theologians have engaged with questions about whether information conservation implies a kind of scientific immortality. These interdisciplinary connections reflect the fundamental nature of the questions raised by the information paradox. The fate of information in black holes touches on the deepest mysteries of existence, consciousness, and meaning that have puzzled human beings throughout history. Looking toward the future, several developments offer hope for further progress. Advances in quantum computing may provide new tools for simulating the complex quantum mechanical systems that govern black hole information processing. Improved gravitational wave detectors might eventually become sensitive enough to detect subtle signatures of quantum gravitational effects. New space-based telescopes could provide more detailed observations of matter falling into black holes. But perhaps the most important developments will be theoretical. The information paradox has already driven revolutionary advances in our understanding of quantum mechanics, gravity, and the nature of space-time itself. These advances have revealed connections between apparently disparate areas of physics that no one had previously suspected. The emergence of holographic principles from black hole physics has influenced research in condensed matter physics, where similar holographic dualities have been discovered in systems ranging from superconductors to quantum magnets. The insights gained from studying black hole information have contributed to advances in quantum error correction that may eventually enable practical quantum computers. The paradox has also revealed the fundamental role of entanglement in holding space-time together, leading to new research programs that explore how geometry itself might emerge from quantum mechanical information processing. These developments suggest that we are approaching a new synthesis in physics, one that unifies quantum mechanics and gravity in ways that earlier generations could not have imagined. Yet the most profound implications of this synthesis remain to be discovered. If space-time is indeed emergent from quantum information, what does this mean for our understanding of time, causality, and free will? If black holes are quantum computers processing information in ways we are only beginning to understand, what other aspects of the universe might be computational in nature? The information paradox has taught us that the universe is far stranger and more interconnected than we had previously believed. The smooth space-time of classical physics gives way to a quantum reality where information, entanglement, and computation play fundamental roles. The boundaries between matter and information, space and time, reality and computation become increasingly blurred. As we continue to probe these mysteries, we are likely to discover that our current understanding represents only the beginning of a much deeper story. The information paradox may be just one aspect of a more comprehensive revolution in physics that will reshape our understanding of everything from the smallest subatomic particles to the largest structures in the cosmos. The questions raised by black holes and information touch on the most fundamental aspects of existence itself. They force us to confront the nature of reality, the meaning of consciousness, and the ultimate fate of everything we know and care about. These are not just technical problems for theoretical physicists, but profound mysteries that affect how we understand our place in the universe. Standing at this edge of knowledge, we can see the outlines of new territories waiting to be explored. The information paradox has opened doors to understanding that we are only beginning to walk through. Behind these doors lie mysteries that may take centuries to unravel fully, insights that could transform not just physics, but our entire conception of what it means to exist in a quantum mechanical universe. The journey that began with the simple question of what happens to information in black holes has led us to the most fundamental questions about the nature of reality itself. We have discovered that information may be more basic than matter and energy, that space-time may be an emergent illusion created by quantum entanglement, and that the universe may be engaged in information processing on scales we are only beginning to comprehend. In the shadow of the black hole lies the deepest question of all. Is the universe a story that can never be erased, or a book whose pages burn forever? The answer may determine not just the fate of information, but the meaning of existence itself. The search for that answer continues, driven by the same curiosity and wonder that has always pushed human knowledge beyond its current boundaries. As we peer into the cosmic darkness where space and time themselves break down, we are reminded that the greatest discoveries often come not from finding answers, but from learning to ask better questions. The information paradox has taught us to ask questions we never knew existed, about the fundamental nature of reality and our place within it. The edge of knowledge is not a barrier but a horizon, always receding as we approach it, always revealing new mysteries beyond. In the quantum realm where black holes process information in ways that challenge our deepest intuitions, we find not the end of physics, but its endless beginning. A reminder that the universe still holds secrets that will continue to amaze and inspire us for generations to come.